So the first session for today is Introduction to Atom Probe Tomography, Principle, Techniques, and Applications. And this is just a very, very short introduction. So if you already have used Atom Probe, if you're somewhat familiar, you might as well go grab a coffee. If you're new to Atom Probe, this is just to tell you, okay, what are we doing when we're doing Atom Probe in principle, so that you later know why do we need to understand how the evaporation physics works, why do we need to understand how the instrument works, and why do we need to understand how to make the samples? Why is that so important? Because, for example, if you go to other to other microscopy techniques and you have an introduction, then maybe people wouldn't spend as much time on sample preparation as we do in Atom Probe. But since in Atom Probe the sample is essentially also the optics, and most materials don't just grow in the shape of an Atom Probe sample, it's very, very important to us that we know how that works. Okay, so what do we do with Atom Probe microscopy, Atom Probe tomography, Atom Probe microscopy? So you might have heard Atom Probe tomography and Atom Probe microscopy interchangeably used. I think the reason Atom Probe microscopy, the name has been pushed in recent years, was that we do more than just tomography. We can do things like orientation mapping. So here we can see an orientation map nanocrystalline material, and so we are more a general microscopy method. Or maybe we do some measurements where there's no tomography involved. If people do surface analysis, for example, just looking at the very surface layers, self-assembled monolayers and so on, then we're not doing tomography anyway. But in general, what we do is we have a solid sample, and solid at the measurement temperature, and we're going to look into what the measurement temperatures are later. A solid sample that we subject to a high electric field, and in fact so high that individual atoms or molecules are ionized and expelled from the sample. So they're ionized, and as soon as they are ionized, they have the same charge as the sample and therefore get repelled. And this is why I said the sample is the optics, because the local electric field on the sample then determines where they are flying. And if you're sort of some tens of nanometers away from the sample, or some hundreds of nanometers away from the sample, that's actually a fairly homogeneous electric field. And so the image that you get is actually fairly reproducible. If you're very, very close to the sample, the field is not as homogeneous, but that's a topic for later today. Okay, but we essentially get a transfer of whatever local electrostatic field we have on the sample onto some macroscopic screen. Now you could make a microscopic screen. You could make a screen that, I don't know, sits 1 micron in front of your sample. I don't know if anyone can come up with a technology like that, but you could do that as well. But our detectors are macroscopic. They're somewhere usually between 40 millimeters and 150 millimeters. And why those are sort of limitations we'll talk about in the instrumentation session. So we have something macroscopic. We've got an image from the sample of the atoms of the sample, in direct connection with something on the nanoscale. And this is where the magnification comes from. And if you look at the tip radii, they're sort of 50 to 100 nanometers. Again, it's something for later. Why? Our screens are a couple of millimeters, a couple of tens of millimeters. So you can see we're in a sort of 10 to the 6 order of magnitude in terms of magnification. But we don't just let them fly at any random time. We let them fly, we let them depart at very specific times. So we need to have a time we can correlate our ions to, and we have a time resolved detector. And this is what allows us to identify which atom is which by the time of flight. And we're going to certainly hammer that home a couple of times during today. Then if we look at that image, we can kind of assume that atoms don't come off from the inside of the specimen. And this is true for the most part. We'll see cases where this is not true, but for the most part this is true. And so we can think of the atom probe experiment as a layer by layer tomography, slice and view, if you will, each slice just being one atom, slice and view on a sort of curved surface. And this gives us the ability to create a 3D reconstruction. And this is where the tomography part comes from. And we can do that on a variety of different materials. So we can do that on metallurgical samples. This is where traditionally we came from. This is an example of hydrogen imaging from the group in Sydney, for example. We have various dislocations and other defects and hydrogen interaction with that. And this here we can just use voltage pulsing. So we can pulse the high voltage and do the experiments that way. But I'm fairly sure that most of you, or a lot of you, are using laser pulse atom probe, because here, in order to couple in voltage pulses, we need a conductive sample. Otherwise, we have a capacitance between the sample and the counter electrode, and that creates fields that will just destroy your sample. This is what we observe if you take a ceramic and try to do voltage atom probe on that. It's not going to live for very long. But with the laser, we can actually do things like non-conductive materials like ceramics, geological materials, semiconductors, and funky things like water. So this is based on atom probe technology. But very importantly these days, we also have good sample preparation techniques based on focused ion beam technology that allow us to essentially make an atom probe sample out of anything that is solid. So we can take a ceramic, we can take a semiconductor, we can take a geological sample and just shape them into a field emitter and do the analysis, and hopefully not destroy what we wanted to look at. And this is being expanded more and more. And one example is expanding it to materials that are not as solid at room temperature. And water is obviously not as solid at room temperature, otherwise we would all be frozen. And our colleagues in Stuttgart have shown that you can actually do atom probe on frozen water. And here the sample preparation is obviously the key, but also having a good laser. Then the other thing that we can have is that we can have materials that are actually smaller than an atom probe sample. Usually we say it's a very small sample, but there are materials that are smaller than even those small samples. And these are nanomaterials, nanoparticles, some nanowires. And here we also have a strong focus on the sample preparation, because the atom probe experiment is actually something that's fairly doable if you have a good sample, but making the sample is the trickery. And this is sort of an excerpt of the research areas that are currently covered with atom probe. Obviously, probably there's probably at least a dozen people here that could raise their hands and say, oh, what I'm doing is not covered here. But I think it's a very good thing. So it's actually being more and more expanded into further areas where we can use atom probe tomography. I think some of the most exciting things that are happening in the chemistry and nanomaterials area, obviously, because that's actually bringing microscopy to where microscopy wasn't really possible before. And I think with hydrogen and materials, it's a similar story. And one thing that I thought was very cool last year was also an example of all of the things together that I've shown you before. Is actually being able to work on highly environmentally sensitive materials and really moving some key technologies forward there. So this is some work that came out of I think Samsung in Korea, where they've done analysis on lithium-ion battery materials, and they've really shown what the degradation of lithium of those batteries looks like on on an atomic scale, or chemically on an atomic scale, and this is really only possible using atom probe tomography, and really utilizes all of the technologies that we've put so much effort in developing in the last years, including sample preparation with the focused ion beam of environmentally sensitive samples, using high-end laser atom probe, and so on and so forth. Yeah. But this is really some of the cool stuff that's going on these days. Yeah. So I hope you're all really motivated now to learn more about atom probe. So where is atom probe tomography? So where do we actually fit in with other characterization techniques? Yeah. So we're counting single atoms coming off of a solid. And so the detection range that we have is essentially just limited by the counting statistics. That's why it says here unphysical region, because if you collect, I don't know, 10, 100 million atoms or something like that, PPT level impurities detection is obviously not a thing, because if you detect a ppm of something, you would probably at least on average have to collect 1 million atoms to at least find one. It'd probably be good if you want to see 1 ppm to have I don't know, 100 million atoms, 200 million atoms, something like that, so they have at least 100 or 200 atoms to count. But essentially it's just counting statistics that limits us. And maybe sometimes we have some artifacts we're going to talk about later, like overlaps, mass spectral overlaps, and so on and so forth. In the lateral resolution region, we're going to discuss that a bit more in depth in the next session. Actually, we're on the nanometer range. Sometimes we can get better than that, but that's usually things that are not that interesting. Sorry to say that. But, it's, for example, if you have pure tungsten, pure aluminum, something like that. But, there's not that much to find in that. There are some exceptions. You might want to look into the architecture of a solid solution, for example, or some very small scale clustering. Then you might be able to get very, very good resolution. But usually it's in the nanometer range. So I'd say 0.5 nanometer to 1.5 nanometers. That's usually our analytical resolution where we stand. Which means high sensitivity, very high spatial resolution, chemical analysis. That's really where we stand. But we are somewhat limited in the volumes that we're getting, and you'll see later in the field of evaporation physics what's limiting us there. And so we typically get data sets that are maybe 100 by 100 by 100 nanometers sort of region, which is 0.1 micron times 0.1 micron times 0.1 micron, or thousands of a cubic micron. Yeah. So you may need to create 1,000 atom probe data sets for 1 cubic micron. So that's not a lot of volume. But you could argue if you go into transmission electron microscopy and really go to atomically resolved transmission electron microscopy, the volumes are even smaller, because you look at a very thin sample. Limited in the area, you're going to be able to look at it, any useful sample, unless you're looking at graphene, where you can, or some 2D materials where you can have a large area. But usually the volumes are even smaller. So if you want to have something where we are volume-wise statistically relevant, usually we go to other techniques like SIMS if you're planar, or some electron microscopy techniques like SEM, STEM, or a microprobe or something like that. So so this is the current status, but obviously atom probe has been evolving for a long time. So most of you know it as probably analytically as a new kid on the block, but really it's been around for a very long time, but only in the last 10 or so years it's really been adopted in materials research on a wide scale, with the reason being that the technology needed to catch up, and there's a variety of aspects of technology that needed to catch up with what we knew what was possible. And those were on the side of sample preparation and on the side of instrumentation. So atom probe or field ion microscopy, which is very close to atom probe, and we're going to talk about that in the next couple of slides, has actually been around since the 1950s and actually has its roots in the 1930s. And there was actually the challenge that how do you visualize atoms, and a couple of different ideas floating around. Especially in the group in Berlin in the 1930s. And one of the ideas by a chap named Erwin Müller, which you'll hopefully all know his name, was to use high fields to image atoms on surfaces. And the reason why high fields could be produced relatively easily is because you can just take a wire and use some electrolyte and create an atomically sharp tip. You can do that at home. You can just take, some drain cleaner or some oven cleaner and a broken light bulb and do that. Or there are actually from a certain guy from NIST, there are papers out there where he did electropolishing in a vodka melon. Yeah, so there's a lot of ways to do that, and you can create an atomically sharp tip. People in scanning transmission, scanning tunneling microscopy even do that with a pair of pliers. Yeah, they use just a pair of pliers and cut iridium is usually, I think, platinum iridium tip at an angle, and they get something atomically sharp as well. So making something atomically sharp is actually relatively easy, and that creates a very high field. And with that very high field, you can do things like creating an image of the electrons that depart the surface, or some ions that are absorbed on the surface. And that's been done in the 1950s, and that was actually the first time mankind was able to image atoms. And but this was using an imaging gas. But already at that time, people observed, okay, there are atoms coming off from the sample itself as well, and essentially you even need that to have a clean surface to look at. And so the question was how to catch that, how to catch those atoms and how to identify them. And the answer came in the late 60s. And in the late 60s, you had something called the atom probe field ion microscope, where the technique was to have a detector that was only time resolved, no spatial resolution, only time resolved, but you could use a little aperture and make sure that you only capture atoms coming from a very small bit of the sample. This is obviously not the end of what you want to do, but because you want to have spatial resolution as well. So in the late 70s, early 80s, people started having spatially resolved detectors, where in the first iteration by John Panitz, you had a detector that could do 2D imaging, but you needed to pre-select the flight times you wanted to analyze. So you needed to know which species you want to look at beforehand. And you couldn't capture everything at the same time. So essentially, you got spatial resolution, but no temporal resolution. So here you got temporal resolution, but no spatial resolution, or chemical resolution, but no spatial resolution. Here you got spatial resolution on a fixed chemical resolution. And then in the mid to late 80s, first a group in Oxford was adapting detectors from astrophysics. And then the group in Rouen was also adopting similar detectors that could then capture both flight time and spatial origin. And so the birth was really the tomographic atom probe in France in Rouen. And you can see from those first papers, you can already see a nice 3D resolution. And you will find out later that actually our reconstruction protocols that we use today pretty much haven't changed very much since this image was first published. Then later on, of course, at that point it was already clear, that a lot of samples that are really interesting, you can't just make by electropolishing. Here with precipitates you can, but for a lot of samples that's not possible. So sample preparation needed to catch up. the first idea to use something that can make atomically sharp tips that's not bound to being electropolishable was using broad ion beams. And after the sample preparation session, you should have understood the physics behind why that is. But you can essentially make sharp tips using just a broad ion beam, just using ion physics. This means you can work on things that are not electrically conductive, and maybe also on coatings and things like that. Yeah. But it's somewhat still unsatisfactory because you want to pick where you want to analyze, and that's been possible using focused ion beam technology. The first publications coming out in the late 90s. At that time, focused ion beams were still rapidly developing, and we had to get a grip on the damage that happens and the techniques and everything. A lot of the protocols were developed that these days we take for granted. So if you're a student starting out, you can take a lot of papers and probably a lot of experience in your own lab and just get started with focused ion beam preparation. That wasn't always the case. And a very, very important addition to that was in the early 2000s to starting to do lift out. So this was just using the focused ion beam to mill the sample. But additionally, with lift out techniques, you actually need to have some way to attach, to grab a sample that you extract from a specimen that you extract from a larger sample and actually make an atom probe tip from that. And that is probably, that is more or less standard of what we do these days. On the instrumentation side, what happened in the early 2000s was very importantly that we moved away from older detector technologies to delay line detectors, which allowed us to have much larger field of view, much better multi-hit detection capability, and we're going to go through those detectors in more detail later. And the other addition that really expanded, and you could even argue led to the explosion of atom probe tomography, was the development of modern pulsed laser atom probe. You will see that the first pulsed laser atom probes already came about in the late 70s, early 80s, but they used lasers that weren't really practical for analysis as we know it today, and that these instruments didn't have spatially resolved detectors. So you had a 1D atom probe, so they were more for fundamental research. But modern laser atom probe, as we know it today, came about both in Japan, in Kazuhiro Hono's lab, and in France, in the Rouen lab at about the same time. And this is a lot of what our modern work is based on. And in the sample preparation, there are still things development, like plasma FIPS have been introduced, so we have a much higher throughput. Sorry, that slide is a little bit older. It was before plasma FIPS were introduced. I made that slide. So now for some of you, that's already, all you've known, all of your PhD. And of course, nanomaterials is still a bit of a challenge. And on the instrumentation side, we're still lacking energy discrimination. So you will see later that there is some artifacts that right now we can't resolve. We're not catching all of the atoms. That's still also something we can't do. And our laser just hit the sample, and we would like them to not hit the sample. This is also something that's very much an ongoing development. So this is not the end of the development cycle. There's still a lot to do in both the instrument development and the sample preparation development. So why is it so very important to understand that? It's so very important to understand that because you will base your work on literature, and you will have to understand that if you read publications, you have to understand what was possible in terms of technology at the time the paper was written. A very trivial thing can be that I've very often seen people find older, not even that old, papers about pulsed laser atom probe, where it says, okay, we did our experiment with pulse energy X and temperature Y, and they don't. When you haven't done that before, you might not know that pulse energy is completely not transferable onto the instrument that you're using currently. Or that if you look at multi-hit data, for example, that wasn't really that much a thing in the older detectors, yeah, because they couldn't resolve multi-hits, and so on and so forth. So you have to understand what technology was available at the time of the publication. It doesn't mean that that the older publications are bad or worthless. It just you need to understand what they were able to know, yeah, because sometimes it's not as explicit in the paper as it maybe should be. And that's maybe also a hint to all of you when you're writing papers. Make sure that your paper still can be understood in 20 years, yeah? When people might not know exactly what machine X did in year Y. Yeah? So maybe try to make your papers a little bit more for eternity rather than just for now. Okay, so what's actually behind the whole technique? So behind the whole technique is the question, how can we image or analyze atoms? Yeah? And essentially you need to have some way to interact with atoms individually. And we can do that, for example, using electrons, and that's something, for example, that's done with electron imaging. Yeah, that's already happened in the 1970s. This is some early images from Albert Crew in Chicago, who had this huge scanning transmission electron microscope with mega electron volts, and there he could make individual uranium atoms visible. They would dance around because of the high energy, but you could make them visible. Or in the 1980s, very famously, Gerd Binning and Heini Rohrer at IBM in Zurich, they used a very sharp tip, which was, by the way, also made using field ion microscopy, to image individual atoms on silicon surfaces. And what these things all have in common is we're exchanging electrons. So we're sending electrons onto a sample surface, through a sample, in one way or another, and extract information for that. If we do electron spectrometry, for example, look at the energy losses those electrons suffer, or the X-rays they cause, or something along those lines. And what those things all have in common is that the electrons that flow do not change the material beyond the local electric fields they create. Ideally, if you blast your sample with a high energy electron beam, you might change your sample as well. But ideally, they don't change the sample. What we do in atom probe tomography and field ion microscopy is a little bit different. We use actually ions, so we use particles with a much larger mass. So the difference is here quantum mechanics plays a large role, because they have a certain wavelength. Here quantum mechanics plays a much smaller role because we have particles with a large mass, ions, that we either use to be ionized on the sample surface, and we'll jump into that later on, or we capture them individually. And this is our information transfer. Our information transfer is we transfer particles from the surface onto some kind of detector and extract information from their flight time, from their location, and maybe potentially from their energy. That has been done before, by the way, but just not in 2 dimensions. If you don't care about 2 dimensions, it's pretty easy to do because you can use a magnetic sector, for example. The group in Berlin has done that for decades, even though they unfortunately don't exist anymore. But that's actually very easy. But in 2D, nobody has done that yet. Okay, and that started in the early 1930s by a guy called Erwin Müller. Erwin Müller was a bit of a special guy, so there's still some people around in the field that knew him personally. And it's always very funny when you talk to them, when the name Erwin Müller comes up. People usually have some unflattering stories to tell, but it's undeniable that he's the father of what we do these days. And he started in the early 1930s trying to find a way to image atoms on surfaces. And he did it by extracting electrons from the surface. Just applying a high field and extracting electrons from the surface. And what he observed was that the image that he got was sort of resembling what you would expect from a block of individual spheres that you try to make into some kind of round surface. So you will see individual flat areas, but not individual atoms. And the reason for that is simply quantum mechanics. So when the electrons come out of the surface, they have a very low energy. So their position is very undefined. And this is the limitation to a resolution of about 2-ish nanometers. Yes, it's close to atomic resolution, but not quite. And so in the 1950s, after World War II, he had moved to the US, to Penn State. And there he has actually developed, changed the polarity. Yeah? So here we've got a negatively polarized sample. Here we've got a positively polarized sample. And in a positively polarized sample, you can introduce an imaging gas. The imaging gas will absorb onto your sample if it's cold enough. Yeah? So the colder your sample is, the better you will have absorption on your surface. And these individual ions then get ionized, and create an image. At that point, they already observed, okay, if I increase the voltage, it's not just the ions that from the imaging gas that are coming off, but I can see individual atoms coming off of the sample. And so how can I analyze them? And so in the mid to late 60s, they developed a thing called the atom probe. And it's called atom probe even though we're not probing anything. It's called atom probe because Mr. Müller was so impressed by Castaing's electron microprobe that he wanted to call his atom thing also a probe, even though we're not using a probe. It's a field evaporation microscope, a field evaporation analyzer, mass spectrometer, or whatever you want to call it. But he called it atom probe, and we're still calling it atom probe today. It consisted an individual tip, cooled using liquid hydrogen. That's for safety reasons not as popular anymore, but at the time that's what you did. You had a big glass cylinder, big glass thing with cooled with liquid hydrogen, and as you can imagine, your safety officer today would probably not be very happy if you say, yeah, I have a high voltage, I have a glass cylinder, and I have something extremely flammable. Yeah, but at the time that was still possible. A vacuum system, so we only get the atoms that are in there, and not contaminant atoms. A field ion microscope, and then you could catch the atoms through the individual time of flight. And everything we do today essentially descends from those instruments. And all of that came out of Erwin Müller's lab. And this is why these developments are so very important for us. And so the most central thing for us is looking at the field emitter. And we're doing it a little bit more in detail in the next session. And essentially, the field emitter is just some kind of needle with a very small radius. And if you derive the field on the surface of a charged sphere, you will see that it's just simply voltage divided by radius. Obviously, we don't have a sphere, so we need to keep our sample steady somewhere in space. So otherwise, we could just take a nanoparticle and make it float somewhere in space and charge it, and it will start emitting ions as well. But we want to have it steady somewhere in space. And this is why we have this needle shape, and we get ion emission only from the area here at the end. In the very early field ion microscopes, here is actually an image of Erwin Müller explaining the field ion microscope. All that was happening was that you had the evacuation, you had your introduction of the imaging gas, very often helium at the time, and then you just have a phosphor. You can build something like that for very, very little money. So all you need is like a wireless phosphor. You can buy that from, I don't know, SPI or something like that for, I think, $100. And then you can make your own field ion microscope. The problem at the time was that the ion currents that you get are on an order that if you have them go directly onto a phosphor, the image is very weak. So in the early days, people were sitting in dark rooms for half an hour, or even a couple of hours, having their eyes accommodate onto the very, very weak image that you get on the screen. So image amplification is a very, very important part of the instrumentation, and we'll talk about that in a bit more detail. So yeah, what does the field ion microscope look like? Yeah, this is one of the early sketches. So you have your liquid. This is German. This is liquid hydrogen. You have your cooling sheath around it, and then you have your tip. You have a pump, and then you have your screen. And the vacuum you actually need to establish to field ion microscopy isn't actually that brutally high. So you usually get away with 10 to the minus 7, 10 to the minus 8, 10 to the minus 9 definitely. If you have a vacuum system with a turbo pump and some rubber gaskets, that's sort of the level of vacuum you can get to anyway. But the vacuum requirements are not as high, just simply because the adsorbed atoms then just come off anyway and just contribute to the image or don't contribute to the image. Anyway, and you don't need to go to extremely high vacuum levels. This actually represents a very nice image of the so these departing ions present a very nice image. It's actually demonstrated here. This is from Drexler and Wolf, an image, a very old image that's you can find in the book by Mike Miller and Richard Forbes, and you can see here. This is a field ion photograph, and here this is just a ball model that they've put together. And you can just simply you can see that the image actually resembles the field ion image resembles this ball arrangement actually very well. If you look at details here, you can see that it's maybe not exactly reproduced, but for the most part, most greater features are actually reproduced fairly well. So you get a pretty nice image of individual atoms on the tip. You might be missing some things. Some things are not as straightforward to interpret, but a lot of things actually are. And as I said, the reason why we can do that so simply is because of the very simple specimen preparation that was used for creating those tips. And all you have to do is just take a wire and use an electrolyte to make it thinner and thinner. And the reason why we do electropolishing in this case is that we can stop the polishing at the right moment. If you imagine you just do that in a chemical polishing agent, it would just keep polishing once you're at the once you already have your atomical sharp tip, and it would make it blunter and blunter. So we're using electropolishing, at least for the most part. Sometimes chemical polishing is actually used, but it's relatively rare. A standard way to do that these days is actually to use some kind of wire-shaped sample that you might have cut out of your material. And then you have your electrolyte on top of an inert liquid, like a liquid polymer. And then you just electropolish it and you get two nice samples. And you may or may not resharpen it in another electrolyte, where you can do that under a microscope observation. We would like to show that to you in our lab, but in the next Atom Probe school we can do that again. Okay, so how do we get to this ionization? And this is just a very very quick excerpt, because we're going to talk about that in detail in the next session. Is essentially that if we have a surface atom and we apply a field, then we reduce the energy barrier significantly for that atom to become an ion and leave the surface. It's a very simplified view. I'm not going to dwell too much on that slide, because we're going to look into that in detail in the next session. But the very important takeaway from that is that we can actually adjust the height of this evaporation barrier by adjusting the field. And the field, as I said earlier, is essentially just voltage divided by specimen radius. Or if you have a specimen of a particular radius, it's just proportional to your voltage. And your voltage is just a knob on your instrument. So if you build your own instrument, maybe it's not that obvious on a commercial instrument, but if you build your own instrument, it's literally just a knob that you can twiddle, you can play with. And I think it's always very interesting when you have students in our lab playing around with the field ion microscope, that they are surprised of how well you can control that just with your own hand. Yeah, how well you can control the behavior of individual atoms just with your hand, twisting a knob. And I think that makes for much of the fascination of the whole technique. Yeah, and this is why we also have our field ion microscope. How does the whole thing look like? And this should, what happened to the video? This is supposed to be a video. This is actually a video from colleagues in Rouen. Sorry, I didn't acknowledge them properly. But they've increased the voltage continuously as they did the experiment. You can see individual atoms of a tungsten tip coming off. You can also see that the field evaporation started at a very, very distinct point. Yeah, as you can see here, nothing's happening, and at some point, bam, it starts. The field evaporation starts. Which means it's a very, very controlled process. And this is great for analysis because it means we can control the field evaporation pretty well. What you can also see is that the image is a slightly bit better before the whole field evaporation starts. And once it starts, you can see it starts looking a little bit foggy. Yeah? And there's actually a physical reason for that, and which is called which is related to the ionization zone. And we're talking about that also in the next session. Okay, so this is our field ion microscope, and this is an image literally just taken with a mobile phone. Yeah, this is just phone shot, and it's very cool because you can have students play around with the field ion microscope. If you look at just a field ion microscope image, already in the 70s, people have done their own work and then have put thoughts into what does the image actually look like. Yeah? If you think that your field emitter is some sort of curved surface, hemisphere, maybe that's a good approximation, maybe not. Yeah? We'll look into that later as well. But some kind of hemisphere, then you can sort of try to work out where in your physical sample your individual atom actually sits. And I've done that here by just taking that image of a tungsten sample and slapped it onto a hemisphere. And you can see the rotation here. And actually, if you look at the atomic planes passing by here, you can see if you just slap it onto some kind of hemisphere, that's actually not too bad an approximation. At least for this specimen here. If you've got different specimens, maybe it's not as good an approximation. And if you, on top of that, look at where they are in Z, you can sort of work out in 3 dimensions where each sample is. And that's sort of the basis of our reconstructions, essentially until today, more or less unchanged. Yeah? The one thing we've obviously added is, as we evaporate the sample, the reference plane, if you will, of where that image is happening moves through your sample. So this is the tomographic aspect of everything. Yeah? That we say, okay, we've removed X volume from our sample. So the plane where this image sits, where we allocate this image, so it moves into the Z direction. But we're going to talk about that in detail tomorrow. And you can actually use that and also for field ion microscopy and do 3D reconstructions. The colleagues in Rouen have really perfected that very, very well. And then you can actually get an image. If you think about, here, you actually get a lot of signal, tens of thousands of ions evaporating, giving you the image of one individual ion. So if you evaporate through a sample, a lot of atoms will be visible at least once. And you get a lot of information from that. And you can do a 3D reconstruction, and you can allocate the individual atoms in 3D then and have a 3D reconstruction with 100% where you see each individual atom, at least in some sub-volume of your sample. And I think this is really brilliant. You can still see, in a lot of areas there's some distortions, Some things are not particularly well reproduced, but there are areas where everything is reproduced. And this is actually brilliant. Okay, and I think I'm going to skip that slide in the interest of time, because we're going to do that in more detail in the next sample anyway. So this was the spatial aspect. So what is the atom probe aspect? The atom probe aspect is actually catching the atoms. Yeah? So we do that using time of flight. Yeah? And the principle behind that is that heavier atoms at a given potential, heavier atoms fly longer than lighter atoms. And we're going to go into the derivation, which is very, very simple, very, very simple. All the derivations in atom probe are actually extremely simple. And that obviously means we need some reference time. Yeah, if we measure time of flight, we need to know when the atom came off of the surface. And we may or may not know that pretty well. There's some inputs there that we may or may not know pretty well. And this is sort of the limitations. But this is the reason why we have laser atom probe and voltage atom probe. Yeah? If you wouldn't need a reference time, you won't need a laser. You wouldn't need a voltage pulse, you wouldn't need a laser. But that also means if you don't have a laser and you want to do some stuff with field evaporation of non-conductors, just switch off the pulsar. You can do that. What we need also is a single atom time resolve detector. And so we need to create a resolvable signal from an individual atom. We'll get into that in the instrumentation session. We need cold temperatures, so that we won't get surface diffusion. You can actually do, if you just want to do analysis, if you just want to know the mass spectrum, there's no need for cold temperatures. You can do that at room temperature. Also, what is cold temperatures is also very individual. It's homologous temperature. Cold temperature for aluminium is something else than cold temperature for tungsten. You can do atom probe of tungsten at room temperature, no problem. The resolution isn't even that bad. Or even field ion microscopy. So we have colleagues here in Erlangen that make a lot of tips for electron spectroscopy using field ion microscopy. They do all of that at room temperature, because it's all tungsten tips. They have no reason to cool anything down. Everything happening at room temperature. And we need an ultra-high vacuum. In the atom probe, we need it for a variety of reasons. The main reason is we want to reduce contamination. The other reason is that if you would be at ambient pressure, there would be a lot of scattering. So we need to have at least a vacuum. And another reason for ultra-high vacuum is that the detectors that we use, they also need ultra-high vacuum, or they need at least high vacuum and ultra-high vacuum in order to properly function. So there's a couple of reasons for ultra-high vacuum. But then it's a very simple time of flight measurement. And I hope by the next atom probe school, we're going to have a very simple setup where you can actually sit there with an oscilloscope and do your own flight time measurements. And this is actually how they were done originally. So there was just simple flight time measurements with an oscilloscope. So this is some traces from Erwin Müller. You can see a reference time, 10 megahertz reference time signal. And then there would be certain channels would accumulate charge, and you would see that here in the histogram, and you could calculate the flight time, and from the flight time what kind of atom that was. Obviously, in this case, you could do some tens of atoms per hour, because you needed to do the traces and then analyze them and so on and so forth. Today, this is all fully automated because we're doing millions of atoms per hour. Obviously, you can't do that by hand. How to get a reference time, I've mentioned it. You can have a laser pulse, or you can have a field pulse. And we're going to get into details of why that is in the next session. How does the mass spectrometry part of it work? Well, you have lighter atoms flying faster, heavier atoms flying slower. And the consideration behind that is actually very, very simple. It's essentially just saying 1/2 mass times velocity squared. This is the kinetic energy of the ion equals the electrostatic energy that we put in. And what do we know here? What do we know? We know what the potential is. We know what voltage we have applied. Sort of. Because if we put in, for example, a voltage pulse, some of that voltage might be transferred to the atom. How much? Yeah, that's actually a good question. So the question in the chat was, does the changing electric field be applied to the sample reflected time of light? Yes, it does. Yeah, it does. This is the reason why many of you have reflectrons, because this energy, this voltage, is obviously changing over time if you do voltage pulsing. And depending on what time during the pulse your atom leaves, it will get a different amount of energy. Yeah. So yeah, we know that with a finite amount of accuracy. Obviously, the charge of an individual electron, we know that with very, very high accuracy. And the charge state, yeah, that's just a number. So it can be 1, 2, 3, 4, 5, whatever, up to 4 usually. We know that with high accuracy. But yeah, we have limited accuracy on that. Then the mass, yeah, that's what we wanted to determine. Obviously, we know that mass is only, we know the masses of individual atoms with very, very high precision, yeah, but we want to measure the mass here. And then we have the velocity, yeah, and the velocity we calculate by flight time. Yeah, so this is our measurement. The flight time can actually be determined with very high accuracy. So modern detectors can do about 200 picoseconds time resolution. Yeah, so we can do that with very high accuracy. And the flight path length is something in your instrument that we can determine. But you will see later that our atoms don't fly in exact straight lines. Yeah, so maybe we don't know the flight path length all as well as we would like it to. Yeah? Or when it comes to laser atom probe, the time that the atoms are actually evaporating isn't all that short either. Yeah, so we might not know the flight time as precise as we like either. Yeah? So these are actually our main limitations here. Yeah? We might not know the potential with absolute exact accuracy. We might not know the flight time with absolute exact accuracy, and we might not know the flight path length with exact accuracy. But if we did, then it's a very simple equation where we have the mass to charge ratio proportional to the square of the ratio between flight time and flight path length. Yeah. But what you can see is we cannot get rid of the fact that we determine the mass to charge ratio, not the mass. Yeah. Which means if two atoms have the same mass to charge ratio, we cannot tell them apart. Yeah. So if you have something that's twice as heavy but also has twice the charge, there's no way to distinguish it. Yeah. At least not without determining what the energy is of the ion. Yeah. If you determine the energy, then you can determine that. But our detectors currently cannot do that. A good example is if you have a molecule evaporating, say O2, O2 2 plus versus O plus. In this principle, there's no way to distinguish that without knowing what the ion energy is. And this might be a very large contribution to why oxygen stoichiometries in oxides are not reproduced very well. Oh, very nice animation pad. Yeah. Here we've got a histogram then plotted of this mass to charge as calculated. That's not the actual mass to charge that the atom has, but it's the mass to charge calculated from our measurement values. Obviously, we know what the mass to charge value of nitrogen plus is, but this is the mass to charge that we measured for our hits, or calculated for our hits. It's not the mass to charge of nitrogen plus. That's very, very well defined. Another thing that you can see here is one thing about our detectors is that we have an extremely high signal to noise ratio. So you can see here the signal, the noise floor isn't even visible. That's why we usually display a specimen mass spectra in logarithmic plot. This is so that we even see the noise floor. Otherwise, you wouldn't even see the noise floor in your plots usually. So what does current instrumentation look like to that end? So very often you have commercial atom probes. So this is a LEAP, commercial chemical LEAP atom probe that we also use in our lab. and in those you have a specimen, you have a small counter electrode, so they can focus your field very, very closely onto your sample. And then you have a cross delay line single ion detector. And we're going to talk a lot about that in the instrumentation session, because understanding how that works and what its limitations are is very crucial to understanding how your instrument, how your data comes about. This is an atom probe that we're operating here in Erlangen. Yeah, it's very similar in setup to a Chemica LEAP atom probe. So you can see here you've got the counter electrode. In this case, it's also a micro electrode. And here you've got your specimen. So here where the hole is, you would have the specimen poking out. Then you've got the cooling braid so that everything is nice and cool. You've got a specimen, a stage to move your samples in 3 dimensions. And here you've got the ability to have a pulse coming in and out of your instrument. And the atoms would then fly off to the right side and hit this detector here. So the famed microchannel plate that we're talking about is this black thing here. Yeah? This is one of those modern fancy microchannel plates with a funnel entrance. And this allows us to have a very, very high detection efficiency, like 80% plus. But again, we're going to talk about that in the instrumentation session in the afternoon a lot. And if you do those measurements, then if you do a measurement on one of those instruments, what you can get is actually a really, really good 3-dimensional reconstruction. I'm sorry, I think this is something either from Bad or from someone else of my former Sydney colleagues, where you can see here in pure iron, and you can see a lot of atoms correctly allocated even down to the atomic plane. And you can do some really interesting things, and a lot of things that have been postulated in terms of material chemistry for a long time have only been shown through atom probe tomography. And here's a very good example for that from the group also in Rouen that have shown the segregation to dislocations, which causes certain mechanical behavior, something called a yielding point by Cottrell atmospheres. And these atmospheres have been postulated in the late 40s already. But it took until the late 90s that really atom probe was able to show that they actually exist in practice. And by now, this is something we see a lot in our data. So by now you might say, it's easy. I can in my bachelor thesis I showed Cottrell clouds. Yeah, but it took a long time to actually have the technology to be able to do that. Okay. And with that, we're actually at the end of the first session. And we're going to have a half-an-hour break, and we are going to continue on at 11 o'clock with the field evaporation physics session.
Sorry, Peter, did you see the question or maybe already answered it?
Yeah, I did answer the question.
Okay, sorry.
The question that came earlier. So if you have got any more questions, just you can ask them as you like. I will stop the recording, so your questions will no longer be on the recording, so you can say whatever you want. You can be as critical as you want. It will not be recorded, so no stupid questions. There are no stupid questions.